So, till now in my previous lectures, I have introduced you to the chirp pulse amplification concept. Okay. And I have told you that this is a relatively new technology that takes the peak powers up to the petawatt level of any glass laser chain or crystalline laser chain. Okay. So, it takes it to the petawatt level, and in fact, and then what happens is the amplifiers become smaller and smaller in size, not individual, but as a whole it becomes smaller in size, and because of this technology, new technology of chirp pulse amplification. And you can have a reasonable sized lab where most of these amplifiers can be placed, and you can get a petawatt level peak powers at the output. In fact, when the power levels reached a terawatt level, such a laser was nicknamed tabletop terawatt laser, T cube laser. Okay. That is because everything fitted into a lab and onto a few tables in a laboratory. Okay. Now, let me go back to the last slide of my last lecture. So, here I had given you this picture of the solid state gain medium and had given you the full width half maximums of the spectrum of many lasing materials. And finally, I said that titanium sapphire and neodymium glass are the most popular, because titanium sapphire has a very large bandwidth, and so does neodymium glass reasonably large bandwidth. And then when we compared the figure of merits of these two, ND glass turned out to be the better one. Okay. And so here I'll just compare once again with some gas laser, just to give you a comparison. And I had said carbon dioxide lasers, laser chain cannot be used because it cannot be reduced to a ultra short pulse. So here is the carbon dioxide laser medium, which has a center wavelength of 10.6 micrometer. Okay. And delta nu is generally given as 1 gigahertz. So the full width half maximums are sometimes given in gigahertz, because that is delta nu, and that is delta lambda is equal to 0.37 nanometer. Okay. Even in this formula, delta T delta nu is equal to 0.32, which happens to correspond to a sec h square pulse. Here delta nu, it is a frequency, but here most of the full width half maximums are given in nanometer. So, these are all the delta lambdas, okay, not delta nus. Okay, it is easily convertible, nu is equal to C by lambda, you can always convert it. So, I go back to my carbon dioxide laser chain. It has a 1 gigahertz bandwidth, which corresponds to 0.37 nanometer bandwidth in the wavelength category. Similarly, for helium neon laser, suppose it is a helium neon lasing medium, it has a center wavelength at 632 nanometer, and the delta nu or the bandwidth in gigahertz is given as 1.2. Delta lambda in terms of nanometer is given as 0.0016 nanometer. So, you can see here that in case of the gas lasers, the bandwidths are very small. So, it is very difficult to get ultra short pulses. So, the crux of the matter is you should have a very large bandwidth in order to get ultra short pulses. So, today let me go on to show you how exactly a oscillator is built. Okay. So, I will talk about the oscillator. So, in the oscillator you are creating an ideal pulse, the pulse that you desire. And what do you desire? You desire a very short pulse that will give you high peak powers, and that means you desire a very large bandwidth, okay, which will give you that ultra short pulse. And then you have to have a nice output spatial profile. That means if you take the cross section of the beam at the output of the oscillator, it should be circular. Okay. So, that is your ideal beam. Such a beam can be amplified and finally recompressed. So, let us go through the oscillator process. Okay. So, here I have already spoken to you about passive mode locking. So, the oscillator is a mode locking technique has been used in order to get those short pulses. So, you have, as I have shown before, you have an active medium and you have a shutter. Okay. You have this shutter between these two mirrors. Okay. This is the schematic or the concept of a mode locked oscillator. And here you have a passive mode locking technique which is taking place, something like a saturable absorber. Okay. So, it is like a nonlinear device and which shows, and this device itself say is a saturable absorber, but because at these high intensities this saturable absorber has to tolerate or has to keep away the care effect which is taking place, not only in this but in the medium also. So, these are all the effects that are taking place. So, here we will concentrate on the saturable absorption process. So, in this case my saturable absorber is a CSAM. Okay. Remember, try to remember in my previous lectures where I described CSAM. CSAM is a semiconductor saturable absorber mirror. Okay. CSAM, M stands for mirror. Okay. SA is saturable absorber and SE is semiconductor. So, it is a semiconductor device which is called a fast saturable absorber. So, this is the concept of the oscillator and this is the actual oscillator. Okay. So, if you were looking on top, from top, you would see all these optical elements within your oscillator itself. Okay. Just have a look at it carefully. It shows a lot of zigzag path, while here in this oscillator between two mirrors, it is very convenient, easy and just going up and down. This is the resonator. Okay. So, here also there is a resonator. So, CSAM forms one end of the resonator. Remember, CSAM is also a mirror. It is a saturable absorber plus a mirror, okay, together. It has been devised in such a way that it can reflect back at the same time, reflect back the pulse or the beam, and at the same time it works as a saturable absorber. So, this is one end mirror like this. Okay. Now, the other end mirror is the output coupler, which is here, which corresponds to this. Okay. These two are the same mirrors. So, you have these two as the two end mirrors. One is the output coupler and one is almost 100% reflecting mirror. Okay. But then in between you have the laser beam is taking all these kind of zigzag path. It is doing all that because I have to include these elements like this prism, then I have to include this mirror. And this is my active medium, AM stands for the active medium. Okay. I have to include all this within my resonator cavity. Okay. So, it is not just straightforward as having one mirror here and one mirror here and the active medium. And I have the pulse, the small pulse, the oscillating pulse revolving between these two. Here what it is doing is it is taking a path like this, like this, like this, like this, like this, like this, like this and back again. So, the path of the beam, of the laser beam inside the cavity is following this kind of a path. These two are also mirrors. Okay, the one shown in brown and this brown, they are mirrors. Just to put this mirror into a small space and to accommodate everything in a nice small manner. And this is the active medium here. Okay. Now, the active medium in this case, in order to, so we are attempting to generate ultra short pulse, that means in the femtosecond range. So, we start off with the mode locking. Okay. So, here what I have is this is the active medium and it is being pumped by diode lasers. Okay. This one could be titanium sapphire. See, I have written active medium could be ND glass or it could be titanium sapphire. Titanium sapphire is attractive because it has a large bandwidth, as I showed you previously. ND glass is a little less attractive in this oscillator, but it has its own advantages. Okay, so, let me assume this is ND glass, okay, and it is pumped by, even titanium sapphire is pumped by some wavelength of the diode laser. So, these are the two diode lasers which are coming in and creating a population inversion in my active medium, one from this side and one from this side. Okay. And these are also mirrors, curved mirrors, which allows this diode laser wavelength to pass through. This also allows the diode laser wavelength to pass through in order to excite the medium in my in the active medium, which say is ND glass. So, now let me start off with telling you how the say a picosecond pulse develops. So, by mode locking I can get in the time range of picoseconds, and I have to still explain how that picosecond will turn into a femtosecond. Okay. So, here what happens is you start off with the initial small photon, small 1 or 2 photons or a little more than that, they collect up and they make it's a small pulse. Okay. So, it is starts off with a spontaneous emission and you get a small pulse which may be like this, shown by the blue line. Okay. Now, this comes to the saturable absorber, this small pulse which may be broad, it comes to this saturable absorber and the saturable absorber acts on it, and as you know, in a saturable absorber the wings get absorbed while the peak remains does not get absorbed at all. So, the peak part is allowed to go through. That is because if you recollect, the saturable absorber works because at low intensities it goes something like this. Okay, this if I call the transmission of the saturable absorber. At low intensities, it is somewhere here, and at high intensities it just does not absorb, it just comes to this. The transmission becomes 1, suppose this is 1, maximum transmission. Okay, this is how a saturable absorber works. Okay. Now, that is because at low intensities you everything is getting absorbed. So, at this part of the pulse, you know, it is getting absorbed, and even the falling edge of the pulse, again the intensity becomes low, that is why it is absorbed. So, that is the characteristic of a saturable absorber. Low intensities are absorbed and high intensities are let through, are passed. So, in this case it is the high intensities are reflected back into the medium, into the cavity. Okay, it comes here. So, now the first pulse which was like this has been shaped a bit of this kind, that means it has become a bit narrow. If you see, the red part is getting absorbed. So, it has become a bit narrow and it has become like this. So, it evolves into this sort of a pulse. Now, in the next round trip, next few round trips, again the same thing is happening. Okay, the wings of the pulse are getting absorbed and the central part where the intensity is higher is let through by the saturable absorber. So, in a saturable absorber, what has to be seen is also this. If you take a two level system, if you remember, go back to the previous lectures and you will remember. So, I have a two level system. So, everything from the ground level goes up to this level. Okay. When the intensity is low, it has just taken up all of them, it has gone there. By the time the intensity, the higher part of the intensity comes, all these molecules here are all here. Okay. So, the higher intensity is let through, but then there is a fast relaxation process also in the semiconductor. So, unless this relaxes back fast, the next pulse will not get the same advantage. Okay. So, these are called fast saturable absorbers also. Okay. So, they have to act quickly. You absorb the molecules from the lower level to the higher level, let the higher intensity pass, and then they fall back again to the lower level. So, by the time the next pulse comes in, you are ready to shape it once again in this sort of a way. Okay. So, it gets shaped like this, and inside the resonator finally you get a very narrow pulse like this, which may be in the picosecond range. Okay. So, this is how your mode locking is happening within this cavity. Okay. Okay, I still have to explain why I need this prism and this prism. Okay. So, here is what is happening. Now comes the nonlinear part, another nonlinear part, which is the self phase modulation. Again, try to remember that, and that is where I talk about this Kerr effect. You know, Kerr effect gives rise to the self phase modulation. Okay. So, this is the part which I have to explain. So, while this small pulse is traveling inside the cavity, it has gathered up, say, enough energy to have, say, somewhere around cavity pulse energy will be around 10 nanojoules to 1 microjoule. Okay. This is, I am not talking about the output. This is the energy of the pulse which is traveling inside that cavity. So, it has grown into a, say, a 1 picosecond pulse, okay, because of the mode locking mechanism. So, I have a pulse energy of this. Then the peak powers will be in the kilowatt to 1 megawatt range. It is all inside that cavity. And then this beam can focus, or you have some elements which will focus it to, say, 100 micrometers. Say approximately, this is just an back of the envelope kind of calculation. So, you focus it to 100 micrometer, then the intensity becomes 10 to the power 8 to 10 to the power 10, okay. 10 to the power 8 to 10 to the power 10 watts per centimeter square. And at these intensities, you cannot escape nonlinearity. The nonlinear part, nonlinearity step in. So, you have the optical Kerr effect which is taking place, and as a consequence of optical Kerr effect, remember, it is the self phase modulation. Okay. So, self phase modulation gives some added spectrum or a frequency chirp. You can go back to those previous lectures and then you will remember self phase modulation gives it changes the profile of the wave packet. Okay. Somewhere I remember I told you this, suppose this is the wave packet. So, you know, it gives some added frequencies here, or basically the chirp is changed. Okay. The chirp is changed here. Okay. That is all because of self phase modulation. This wave packet is given a new kind of a dimension like that. So, there is either you can say there is an added spectrum. So, you have added some new frequencies to the already existing spectrum, and the moment you do that, that means your pulse is getting shorter. The moment the spectrum becomes larger, you have added some spectrum, accordingly the pulse in time, the temporal pulse becomes shorter. Okay. Now, the moment the temporal pulse becomes shorter, GVD comes into the picture. Okay. So, this is all happening within this cavity. Okay. So, now because the intensity has grown that much to the 10 to the power 10 watts per centimeter square, you are getting self phase modulation, which shortens the pulse. So, you already have a picosecond pulse which is going around, and at the same time simultaneously during that time itself, because the intensity has gone up, self phase modulation comes into the picture. And the moment self phase modulation comes into the picture, your pulse becomes shorter than the picosecond. But there is a problematic part. The moment you make the pulse shorter and shorter, group velocity dispersion comes into the picture again. So, as you remember in my previous few lectures, group velocity dispersion means all the wavelengths or all the frequencies within that pulse start to diverge out. The different wavelengths travel at different speeds. Because they travel in different speeds, there is a phase change which is brought about between all these frequencies. So, you have two competing things happening: self phase modulation, which is reducing the pulse length, but when you reduce the pulse length, your spectrum is increasing. So, your group velocity dispersion is also increasing. But what does the group velocity dispersion do? The group velocity dispersion will lengthen the pulse in time, and you do not want that in your oscillator. You are aiming for a very short pulse, but you are getting a longer pulse. So, it has to be somehow avoided. So, generally group velocity dispersion, as we have seen before, it can be controlled with the help of grating or prisms. So, in case of an oscillator, they use two prisms, whose these faces are parallel to each other, and you are able to control the dispersion. So, suppose at this part all the wavelengths are dispersing off in some way. This gives you a angular dispersion which brings it back. These two together brings back that dispersion, which spreads out the pulse. You sort of control the dispersion by changing the angle between these two prisms or the distance between these two. So, these two have to be included within your resonator cavity. That is why your resonator does not remain as simple as this, just two mirrors here and the active medium. It becomes complicated because of the addition of this. Okay. And we have to tolerate that complication, because after all we are looking for ultra short pulses. Okay. So, finally, after many round trips, the self phase modulation and the group velocity dispersion are working in a sense complementary or against, however you may call it, against each other, and it comes to an equilibrium position where finally the group velocity dispersion in one round trip becomes 0. Okay. So, there is a equilibrium point between these two phenomena that are happening: self phase modulation and group velocity dispersion. Okay. They counter each other and come to some point, and that is the point where when you get this femtosecond pulse. So, you have been able to reduce it from, say, a picosecond pulse, which happens in any kind of mode locking, and you have been able to shape that picosecond pulse into a femtosecond pulse. Okay. So, generally out of this oscillator, you generally get a whole lot of pulses like that, a train of pulses of this kind. From an oscillator that I described, this you get a train of pulses. So, in each round trip, after it has come to an equilibrium position of the pulse, you get this train of pulses, and all of them have the same pulse width in the femtosecond range. Okay. And what you can measure outside is an average power. If you just put a detector there which is measuring the output pulse, you will get an average power. That is because that is what you want to measure here. So, you get a train of pulses, you get average power. Average power is, if you remember, pulse energy joules into rep rate. Okay. So, these are always at a repetition rate, these kind of oscillators. Each pulse is in the femtosecond range, but they come with a repetition rate. Okay. So, that is why you get this train of pulses. So, in case of ND glass, you may get an output of 50 milliwatt. In case of Ti sapphire, these are some typical values. You may get an output of 200 milliwatt out of this oscillator. Okay. So, this milliwatt is the average power. This milliwatt is the average power. So, that is what you get output. Now, but then we are actually interested in just one pulse, because we will get peak powers with this one pulse. Okay. The energy will be divided by this time and we will get a high peak power. Okay. So, we will have to select just one pulse out of all of them. It is not very difficult, it is easy to select. So, as you can see here, self phase modulation causes the pulse spectrum to broaden. The added spectrum makes the circulating pulse shorter. Okay. A shorter pulse is more prone to GVD and therefore detrimental to the generation of short temporal pulse. The interaction of SPM and GVD can be exploited in such a way as to obtain a short pulse. The prisms are dispersive elements in the laser cavity that provides adjustable GVD. Okay. This is in short whatever I have explained. So, we will go on further with this.